Assalamu alaikum warahmatullahi wabarakatuh. Hope a good day for everyone. Today I'm going to talk about light emitting diodes for electronic devices, prepared by Shawdari Marwa and Noor Fatima binti Abdurrahman. Let's talk about device configuration. This is the definition. A light emitting diode LED is a semiconductor B junction device that emits light when forward biased. Main components are B-type semiconductor, N-type semiconductor, p junction, anode, positive terminals, cathode, negative terminals, and encapsulation. Materials used gallium-based components like gallium arsenide, gallium phosphide, and gallium nitride. Material determines color of light emitted. Now let's talk about physical structures. Small semiconductor chips are mounted in a reflector cup covered with transparent coating to enhance light output. Let's move to basic operation of the diode. Forward bias operations. LED operates only in forward bias. Positive voltage applied to anode and negative voltage applied to cathode. Electron hole recombination. Electrons from N-type moves to P-type, and holes from P-type moves to N-type. Recombination releases energy as light, photons. Light emission. Energy releases when electrons drop to a lower energy level. They release their extra energy as visible light. Color depends on band gap energy. Color depends on band gap energy. The size of the gap between energy levels depends on a specific color of the LED. A higher band gap means a shorter wavelength. A higher band gap, a large gap means high energy, which produce short wavelengths. Colors light blue. Lower band gap, longer wavelength. Lower band gap, a small gap means lower energy, resulting in longer wavelength. Colors like red. Okay, from this slide, I will let my friend to start.
Next, I will explain the characteristics of the device focusing on light emitting diodes or LEDs. First, let us look at the current voltage or IV characteristics. LEDs exhibit a highly nonlinear diode-like IV relationship. This means that a minimum forward voltage must be applied before the LED can emit light. Typically, this forward voltage ranges from about 1.2 volts for red LEDs to around 3.6 volts for blue or white LEDs. Once this voltage is reached, the light intensity produced by the LED is approximately proportional to the forward current flowing through it. Next is luminous efficiency. LEDs have very high luminous efficiency, measured in lumens per watt. Commercial white LEDs can exceed 150 to 200 lumens per watt, making them significantly more energy efficient than conventional lighting sources. However, LED performance is strongly affected by temperature. As the junction temperature increases, the luminous flux decreases. The emission spectrum shifts towards longer wavelengths, also known as redshift, and the lifespan of the LED is greatly reduced. Therefore, effective thermal management is critical to ensure reliability and long-term operation. One important limitation of LEDs is known as efficiency droop. This refers to the reduction in internal quantum efficiency. When LEDs operate at high current densities, this phenomenon is commonly attributed to non-radioactive Auger recombination, while limits efficiency at high operating currents. Next, I will explain about future development limitation and sustainable engineering considerations. Looking at future developments, one major area is micro LED technology. Micro LEDs offer ultra high resolution and high power efficiency, making them suitable for next generation consumer electronics. as well as augmented and virtual reality applications. Another important development is the integration of LEDs with the Internet of Things or IoT. Due to their small size, digital nature, and controllability, LEDs can be easily integrated into smart lighting systems, enabling adaptive and energy efficient infrastructure in smart cities. In addition, research in ongoing invisible light communication, also known as Li-Fi, this technology uses the fast-switching capability of LEDs to transmit data at high speeds using visible light. Despite these advantages, LEDs still face several limitations. Firstly, thermal management remains a major challenge. The need for effective heat dissipation increases the complexity, size, and cost of LED luminaire designs. Secondly, the reliability of the driver circuitry is a concern. In many cases, the lifespan of an LED lamp is limited by the electronic driver rather than the LED chip itself. Lastly, although color rendering has improved, achieving a perfectly continuous spectrum similar to the natural sunlight while maintaining high efficiency remains difficult. From a sustainable engineering perspective, LEDs offer significant environmental benefits. Their high energy efficiency reduces electricity consumption and lowers carbon emissions. However, material resource management is an important concern. LEDs rely on critical and sometimes scarce materials such as rare earth, phosphorus, indium, and gallium. Sustainable engineering therefore requires the development of effective recycling methods and alternative material to support a circular economy. Finally, mitigating light pollution is essential. Responsible lighting design involves using appropriate spectra such as warmer colorated color temperature and precise optical control to minimize light pollution and reduce negative impacts on human health and wildlife. That's all from us. Thank you.